A gas turbine power plant may appear simple from the outside: a turbine, a generator, and an exhaust stack. But inside, it is a carefully balanced system that converts fuel into electricity through continuous energy flow. Unlike piston engines that rely on repeated explosions, a gas turbine produces power smoothly and constantly, making it one of the most important technologies for modern electricity generation. At the heart of a gas turbine power plant is the Brayton cycle, which operates through continuous air compression, combustion, expansion, and exhaust. This cycle allows the turbine to deliver stable mechanical power that can be directly converted into electrical energy. The process begins with air intake. Large volumes of ambient air are drawn into the turbine through filters that remove dust, moisture, and contaminants. Clean air is essential because even small particles can damage compressor blades over long operating periods. The airflow is steady and uninterrupted, forming the foundation of the entire system. Next comes the compression stage. The incoming air enters a multi-stage axial or centrifugal compressor mounted on a common shaft with the turbine. As the compressor rotates, rows of blades progressively squeeze the air, increasing its pressure and temperature. This step requires significant energy, which is why part of the turbine's output is always used to keep the compressor running. By the end of compression, the air may be pressurized to many times atmospheric pressure. The compressed air then flows into the combustion chamber. Here, fuel, most commonly natural gas, but sometimes diesel or other fuels, is injected and ignited. Combustion occurs continuously and in a controlled manner. Unlike the violent explosions inside piston engines, the flame in a gas turbine is stable and sustained. The key objective is to raise the temperature of the air dramatically while keeping pressure nearly constant. Chemical energy from the fuel is transformed into thermal energy stored in the hot gas. This high-temperature, high-energy gas is directed into the turbine section. As the gas expands through rows of turbine blades, it transfers energy to the rotating shaft. The turbine extracts enough energy to drive the compressor at the front of the engine, ensuring continuous airflow. Any remaining energy becomes useful mechanical output. In a power plant, this output is what ultimately generates electricity. The turbine shaft is directly connected to an electrical generator. As the shaft spins, it turns the generator rotor inside a magnetic field. This motion induces an electric current in the stator windings, producing electricity. The turbine is typically operated at a constant speed, synchronized with the electrical grid frequency, ensuring stable power output. After passing through the turbine, the gas exits through the exhaust system. Even after energy extraction, the exhaust remains extremely hot. In a simple cycle gas turbine plant, this hot gas is released to the atmosphere, and the electricity generated comes solely from the gas turbine itself. However, many modern power plants use a combined cycle configuration to improve efficiency. In this setup, exhaust heat from the gas turbine is captured in a heat recovery steam generator. The waste heat produces steam, which drives a steam turbine connected to a second generator. This allows the plant to extract additional energy from the same fuel, dramatically increasing overall efficiency without burning more fuel. Cooling and temperature control are critical throughout the process. Turbine components operate in extreme thermal environments, often hotter than the melting point of the metal itself. To survive, turbine blades are made from advanced superalloys and cooled internally using air bled from the compressor. Precise fuel control systems regulate combustion temperature to protect components and maintain long service life. Gas turbine power plants are valued for their fast startup and flexible operation. Compared to coal or nuclear plants, gas turbines can reach full power quickly, making them ideal for balancing electrical grids with fluctuating demand. This responsiveness is especially important when supporting renewable energy sources such as wind and solar, which vary with weather conditions. Fuel flexibility is another advantage. Many gas turbines can operate on different fuels with minimal modification, allowing power plants to adapt to fuel availability and cost. This flexibility enhances energy security and operational resilience. In summary, a gas turbine generates electricity by continuously compressing air, burning fuel to add heat, and expanding hot gas through a turbine. Convert that power into electrical energy through a generator. Whether operating alone or as part of a combined cycle system, the gas turbine is a highly efficient, reliable, and versatile solution for modern power generation. It transforms the principles of thermodynamics into the electricity that powers industries, cities, and everyday life.